have a quick recap of inverse functions that we saw earlier this year. A reminder, if there is a one-to-one relationship between the two sets of data, then both the relation and the inverse relation will be functions. It'll satisfy both the vertical and the horizontal line test. And in that case, we call the inverse relation an inverse function. Now remember, a function could be either one-to-one or many-to-one, but it's only the ones that are one-to-one that will have an inverse function. And if it is one-to-one, then we know this relationship exists because inverses will cancel each other out. If I substitute the inverse into the function, or if I substitute the function into the inverse, I should simply get x. How do we test? Let's say there's the line test, the horizontal line test to test for inverses. The other way is rearranging our formula. So we swap the x and the y's around, make y the subject. If we get something that is unique, then we know we've got an inverse function. The inverse function of an odd function will always be odd. And that's because every odd function goes through the origin, if it exists at x equals 0. Because obviously the hyperbola is an odd function, but it doesn't go through the origin, but it also doesn't exist at x equals 0. Otherwise, it has to. And it has to because of the rotational symmetry of the odd function. Whereas even functions will never have an inverse function, because inverse functions have reflectional symmetries. Well, as soon as you've got reflectional symmetry, you're going to fail the horizontal line test. So no even functions will have inverse functions. Domain and range, well, if we know the point AB is on our original function, then BA, swap the x and y's around, must be on the inverse function. That basically means the domain and the range swap around. So the domain of the original function is the range of the inverse function, and vice versa. Well, we've been talking about exponentials. Let's look at this one then. Y equals e to the power of x, there it is. We can see domain is all real x. Y is greater than 0. It is a one-to-one function, so we'll have an inverse. Swap the x and the y's round. X equals e to the power of y, which we know we can rewrite as y equals the natural log of x. And the domain of natural log of x, yeah, that's x is greater than 0, and the range is all real y. The domain and range have indeed swapped around. If we were to draw it, remember the inverse and the function should be reflections of each other in the line y equals x. There's our log curve. But when you think about it, there's not going to be a lot of functions that we can find inverses for. If we restrict to the only ones that are one-to-one, we're basically looking at something that is continually increasing or continually decreasing. Because as soon as it turns, you're going to fail the horizontal line test. So that cuts out a lot of functions. For that reason, what we tend to do is restrict the domain. And we just look at a piece of the function that we can use to create an inverse function. Now, how do we choose that piece? Again, we're looking for a piece of the graph which is continually increasing or continually decreasing. That's the piece we would be interested in. There's obviously going to be lots of different pieces you could pick. So we tend to try and include 0 if we can, and maybe we go more towards the positive numbers than the negative numbers. But it doesn't have to be that, it just sort of tends to be what we do. So let's look at the most basic even function that we know, y equals x squared. Its domain's all real x, its range is y is greater than or equal to 0, but clearly it's not going to have an inverse. I want to pick a piece of this which is continually increasing or continually decreasing. I'm going to go with the positives. If I go with x is greater than or equal to 0, I now have a piece of that curve which is continually increasing. My range has not changed. That's the nice thing. If we can keep the range the same with the restriction, then that's good. Inverse, swap the x and the y's round, I'll get y equals x to the power of a half, or the positive square root of x if you prefer. The domain would be x is greater than or equal to 0. The range, y is greater than or equal to 0. Yeah, possibly not the best example to show you this, because look, the domain has changed to the range and the range has changed to the domain. Well, they were the same anyway, but oh well. If we were to draw it, there we go. The top half of our parabola, a reflection in the line y equals x. Let's have a look at this old HSC question. Here's the function e to the minus x squared. The graph has 2 points of inflection. All right, we haven't really talked that much about inflections at this stage, but that's basically where it changes concavity. Changes from concave up to concave down, or vice versa. Twists is another way of thinking about it. find the x coordinates of these points, and what we will find is that, well, if we're investigating, looking for inflection points, the key is looking for when the second derivative is equal to 0, because concavity is measured by the second derivative. So if it changes from positive to negative, then it has to pass through 0. So we look for that. Second derivative, again, not something we've really talked about yet. It simply is when you differentiate for a second time. So I'd have to use my product rule here, write down the first if the second, plus write down the second if the first, and I come up with that expression. If I want to solve that to be equal to 0, well, clearly the exponential part can't equal 0. It's just the 4x squared minus 2, and I get my two possibilities. But because they've given me the graph, I can say, well, yeah, okay, yeah, there are two. I've found two possibilities. They must be the two. The x is plus or minus 1 on the square root of 2. Explain why the domain must be restricted. Let's go back to that idea. Well, I need the function to be 1 to 1, or I need it to be continually increasing or continually decreasing, whatever words you choose to use, but that's the sort of thing they're looking for, that you understand, hey, we need a piece of the curve that does this. Find a formula. Weird way of saying it. Why didn't they just say find an equation? But anyway, find a formula for the inverse function of x if we restrict our domain to be x is greater than or equal to 0. Swap the x and the y around. Now, when I make y the subject of this, of course I get plus or minus the square root of the log of 1 on x. That, of course, is not a function because we've got, well, the answer is not unique. I've got plus or minus. The question now becomes, which one do I take for my one? The positive square root or the negative square root? And that comes down to how we restricted it, because my restricted domain will become the new range. So if my new range will be y is greater than or equal to 0, I must have the positive square root. So that's the equation or the formula for our inverse function. State the domain then. The range will become the domain. From the graph I can see that the original range was between 0 and 1, not including 0, so therefore that becomes the domain of my inverse. And then they asked us to sketch it. Okay, I might have cheated and just rotated their curve, but you would just draw in that sort of shape to get the reflection in the line y equals x. So there's a little recap on inverses before tomorrow we can look at the inverse trig functions, which we're interested in.